And let's get started. Hello, everyone. Welcome. Today, today's lecture will be about clustering, and for all the materials that are covered in this class, I mean all the R file and the lecture, the slides will be in this link. You will find this here, and also you can find the video and actually the recording afterwards. And no more chat. Let's come to today's topic. Today we are going to talk about clustering. And before coming here, and I see the quick quiz for students in the classroom. Who has ever heard of the clustering? Please raise your hand. Anyone who has heard of that? Yeah, okay. And some yes and some no. Good. And so first question, we will do a quick review on what is clustering. And since a lot of you have already known that, and the first question is for you, and you will try to give a definition on that. But before that, for those who haven't tried or get familiar with those topics, we can see that in the figure there are, sorry, 1 second. I think online students are seeing a smaller figure. Oops. Use side. I think in this way, both online students and in-class students can see the larger scale. And here we have a picture on all the data sets. We can see the data set itself there has some structures. Some dots or some points or some data are closer to some else in the cluster. And then we can see that the latent or the underlying structure of them, all those within the same color may be more subclustered or more similar to each other, and this procedure is so-called the clustering. And then students, for those in-class students, anyone who want to try to give a definition of the clustering, it's just to use your own words to repeat the procedure, and then we can show the definition of the clustering, and you can see how well you organize that and how well you didn't do that. Anyone want to try?
Put the things with similar features together?
Put the things of the similar features together, right? Okay, let's see how far you are with the definition of that. And here, clustering, the group projects into subsets or clusters. So you need a subject for that, for the definition. You need the objects or the data. And such that the objects within each clusters are more similar to one another than the objects assigned to different clusters. You see that? Okay. And since most of you have already known the clustering, and then there's a question about the difference between clustering and classifications. Any idea?
The class of classification is already known. For clustering, we don't know.
Okay, you mean for the classified data, you already have the class or they are already labeled. And on the other hand, for the clustering, we are either not known or it's not really necessary, right? Or so-called label, unlabeled. And other difference?
I mean, I'm still pretty new to this, but it seems to me that clustering is to, like you said, group like a bunch of subjects into one cluster, whereas classification is to take one object and like give it a certain
You mean like for clustering, it's more like you are kind of paralleling or grouping different sets, And for classification, it's more like for one data set, you are giving a target for it. Is that you see? Yeah, that's a good point. That's a good point. And from different perspective, one is from the overall general, and one is from the single data points, right? I love your point. Thank you. And I do mention two main differences here. And the one is already mentioned, the labeled and unlabeled. And another thing is also very popular in current research is learn and apply. And for the data, sometimes we know that after get the raw data, we first need to, from the overall perspective, we need to do the clustering and see the patterns, as you just mentioned. That is from the overall or general perspective. And then we kind of wanna, after learning, we're trying to apply the structures and into future, and then keep using it for new data, and which is a combination of few things. And this is super powerful and popular nowadays because of the three nouns. I think some of you might already heard of that. The first one is supervised learning, and second one is unsupervised learning, and the third one is semi-supervised learning. And especially for the third one. And nowadays, with bigger and bigger data, not all the data have already been labeled. And some of the data take a very long time for human to label them, or so-called annotate them. And so the current the up-to-date research strategy is to label part of the data and then use them to get the information to learn and then apply them for future things. See? Okay, and what is clustering? On the above part, I recall the goal here and group projects into subsets of the clusters such that the objects within clusters are more similar to one another than the objects assigned to different clusters. And here, one of the important words I make it bold and underline, which is similar. And here, there might be different definitions about the similar. But another question very urgently is that how to measure the similarity. And there's one thing we can do is to measure the distance. And there are a lot of ways to measure the distance, but before going to any of the distance, is there any distance that in your mind, or when you talk about distance, you will come to your mind? Even though we can see them one by one. But again, I think, again, I do like to emphasize that it is with practicing, with speaking, and you can memorize all these materials even more. And I know that for some of the material might be easier for you, but you think you already control that or understand that, but try to practice more and give you a better understanding, okay? First measurement on distance is the Euclidean distance. And on the left, I ask 3 questions from easier to hard. And the first one is, who is Euclid? And the second is, what is the Euclidean distance? And the third one is how to write them down in math. And for the first one, have you ever heard of the name of this person? Yes or no? Yep. Yeah, I see a lot of Chinese students in the classroom and the online students. In Chinese, is Oji Lide. So we know that is a great mathematician and invented a lot of, especially in the geometry. And there are different geometries. I think there might be questions. Or maybe not. Okay, and if there are further questions, I will discuss them at the end of the lecture. And then when talking about different geometry styles, actually Euclidean geometry is one of the most famous ones. And we can see that on the right top corner, there are different geometry styles. On the first one is the one that we are most familiar with, which is raised by Euclid. And we are saying that the plane is a plane, it's not curl anymore. Okay? And in this case, we will have different theorem. So for example, like the inner triangle of the triangle is the 180 degree and things like that. But these positive results are not really true for other curvatures and other geometries. But we know that in different geometries, the distance could be different. For example, the second one is super helpful in measuring the globes or the spheres. We know that we live in the Earth, which is more like a globe or a sphere like this. So when measuring the distance for 2 points, for example, from Beijing to New York City, Euclidean's plane or the distance on that green is not really helpful. There's a big mistake on that. And we need to use different distance calculations, okay? And it's the same for that. But here, first of all, we are talking about the Euclidean distance. And we all know this picture on the right bottom. This is, this I think in China discovers even earlier so-called 勾股定理, and in English or in Greece also the Pythagoreans also discovered the relationship between this. And we mention this because this is maybe the most common way to calculate the distance in the two or the so-called orthogonal coordinates. For example, we have two dots, A and B. For A, we have the coordinates x1, y1, and for B, we have x2, y2. So is there anyone wanna say or come here to write down the distance between A and B? And actually, we are right now on the third level. We are trying to write them down in math, and which I think most of you or maybe all of you need some more practice on that. So anyone want to give a try on measuring the distance between A and B? Thank you.
So A and B, I think, is this is A and B, right?
Yeah.
Okay. So for A and B, is x1 minus x2. Things that.
Okay, and that's already perfect. And can you even push it further to use sigma instead? I mean, sigma is the sum of the things, right?
Maybe like this.
Yep.
Maybe like.
Give a try.
I1 xi minus x1I minus x2I and has like n power and this like this.
Yes and no. First, why is no? Or anyone can help her with correcting this formula?
This is different.
Okay.
This is not n. Actually.
Yeah, just for this case, just write about 2 is fine. Just about 2 is fine.
Yeah, and 2. This is n.
Okay, great. And thank you. And any other students? Do you think this is right or wrong?
No, I mean, there might be something wrong with the collaborative classroom.
Oh.
Because students cannot see the screen.
Oh. Can you see now? Sorry. Okay, sorry. And right now we are on the slides. Okay, we can go a very brief review on this. And sorry for the online students. And this is the slides we just got started. Today we are talking about the clustering. And first of all, this is the definition on that. And also thank you. And this is the definition on this. And then we are talking about the difference between the clustering and the classification. And then in the definition of the clustering, and we can see that the most important is the similarity and the distance. And let me know if they are asking something. Okay. Yeah. And then here we are talking about the first thing that we can measure the distance is the Euclidean distance. And here we talk about how to calculate that. And in-class students.
Excuse me.
Hello?
The screen is not seen again.
Okay. Oh, I think one might be wrong. There are two screens, and we can keep them the same. You can then see the screen. I think they are already. Can you see this right now? You can talk. Okay. But you can see now, right? It's like when I am not doing a presentation, you can see that, right? Can they see this? No, you can only show the class online. Share application. Just application. I think this time you can see the slides, or we can try this. Can you see this?
Now we can see it.
Okay, great. And this time I'm sharing the slides and only, but that will cause some problem in the art section, but we will solve that later. And for now, then we are talking about the distance, especially the first distance in the coordinates. And thank you, Gordon, for writing the formula here, and which is 100% correct. And my suggestion is that try to use more mathematical descriptions on that, and because that is the easiest way and the only way to implement this into the computer or the softwares. And here, this is, and also after that, this is a two-dimensional. We see that the dots. And any other students, for example, I only have one number axis. Anyone can give the distance for these two dots, A and B? And anyone want to give a try? In-class students? Yes, but can you come around and write that down? Because these two formulas are super important. And that's better. And yeah, okay, thank you. And any other suggestions or comments on that formula, or anyone wanna? It's almost there, but there can be some more correction or the perfectizations.
So it's absolute value between x2 and x1, right?
Can you try to modify that on the blackboard? Thank you. Okay, great. Thank you. And you see the difference between that?
Yeah, I'm sorry.
No. And this is also important. And we can see that this is on the first dimensional or only one dimensional. And the one that Gordon just read is on the two orders or two dimensional. And this is super important because you might have ever heard of this or you might not, but this is super important. L1 norm, L2 norm, and L infinity norm. And they are different ways in calculating the distance in different norms or the different coordinates. And we are maybe more familiar with the L2 norms. And in this case, we can see the square. We can do the subtractions and do the square and do the sum and take the square root. And for the first norm, we just take the abstract and do the absolute value and take the sum. And also there's even L infinity normals. There are different ways to do the calculations. And there are some examples. We can see that take a point of V at the coordinates of 1, 2, 3, and we can see that in the different L norms, the distance could be different. And I do give the ways to calculate. We can see the numbers. For L1 norm, this is 6, and then to X infinity norm, it is around 3. Okay? Any questions so far? And also, we can try to use the geometry of the figures to discuss or to visualize these lines. In L1, actually, we only talk about the sum of the x1 and x2, even the sum of all features. So it is almost linear. So we can see that it is in this square coordinate, it is like a square that on the left. And when it is L2, and it's more like a circle. Okay, and for each dot on the circle self, the distance is the same, and that is the distance of the L2 norm. Okay, any questions so far? Why this is so important? The secret lies in the figures on the right. Let's see that again. L1 and L2 norms are very important in evaluating the loss. I think last lecture we talked about the loss function. And again, in class students who hasn't ever heard of the loss function before, who hasn't do that? Okay, loss function is the distance between the true values and your predictions. So we do really wanted to lower or make it minimize the loss functions. And then we will set a threshold for the loss functions until it's less than like 10 to the minus 7, for example, and we say it's already converged, and say we say good, it's already a good enough model or the model things, okay? But in doing the different simulation or when having the different machine learning algorithms, the loss functions are different. And some of them are using the L1 norm, some using the L2 norm. And by using the L1 norm or L2 norm, we can see in this picture, all the blue parts are the errors. You see, for example, we set a small number epsilon, and all that the small epsilon smaller than that is inside either inside the circle or inside the square, and those are the that's are the error functions or loss functions or the small things. And the figure or the curves above is the things that you are trying to do the modification or trying to do the modeling. and you are kind of enlarging or smalling, and then until you found the thing, you point the point that already they converge, and then that is your model. Okay, and we also see that with different loss functions, the final results are different. Okay, for example, in class students, you can see that for L1 norm, the line stops here, but this model stops here. So for this one has the smaller error, even though they are setting the same threshold of the distance, but using the different distance calculations, the results could be different. Okay. Okay, too much about the Euclid, and then we are talking about different other distance. This distance is about the J-car distance. On the screen, there's the description of that. J-car distance is first raised up for sets. So we can see that how to measure the distance between different sets. There's an example on that. And there are two sets, ACDE and ADE. And on the right, we can do the calculation. First is the conjunction of them. They do what they have in common. We see that there are 3 letters or 3 elements inside, which is ADE, and that is in common. And then then the union for that is all the elements that appeared in both sets, which in this case is ACDE. There are 4 of them. So the distance here is 1 minus 3 divided by 4. Okay? And this is one way to do the distance between the sets. And this is especially powerful or unexpected powerful because there are other applications. Is there any other application that you can have in your mind? If no, there are some applications. J-car distance also measure the distance between the sentences based on the words. For example, I have 2 sentences. The first one is I love you. The second is I love you too. And using the same distance measurement, we can calculate even the distance between 2 sentences. See what I mean? Yeah. And also, what's even more, we can also use this method to calculate the distance between the movies and restaurants based on their ratings. As long as they can be expressed in a set expressions, they could use this way to calculate the distance. Okay? Okay, great. And again, all those distance measurement methods are only the distance. And you, in your real project, you will see which can really best measure the distance or see the characteristics. Okay, and here we are just not saying which one is better, but we are just introducing all the measures. And then next one is the Hamming distance. The Hamming distance is to calculate the distance between 2 strings of the same length. Number of the positions at which the corresponding symbols are different. For example, there are 2 strings talking about that. The first one is like Caroline, and then is the Catherine. We can see that the color part are the different parts. So when measuring 2 string things, we can measure those unpaired or different parts and measure the length of that. Okay, and also the same one also measure to that binary string for that 101101, and also the other. And we can measure the distance between that. How many digits or how many positions are different, and calculate the positions in total, and then that can be the difference. Okay. However, this method has its drawbacks. It requires that both strings should be of the same length. Otherwise, it cannot be calculated. Even though the length should be different, should be the same, you could still think about the distance about very important things like test DNA and even for the protein sequence. And because in the DNA and proteins, sometimes we can measure of the same difference. For example, we can see the unit are usually of the 3 digits, like UGA or things like that, because they are always 3 or 3 the times of the 3s, so they are more comparable to each other. See what I mean? So this is usually helpful in the biology and the biomedical researches. But we're not really satisfied when comparing those same length distance. we are really interested in sometimes the different lengths of the strings. And how to do that? We can do the edit distance. Here, edit distance is defined by using the number of inserts or deletes to change one string into another. For example, there are A, B, C, D, E, and Y here. The distance could be what is the minimum things that we can change from X to Y. In this case, we can start from X, and by first step, we delete A, and we got B, C, D, E. And then we insert U and insert a V, and then we get Y. So the distance could be 3. Okay? And that is the case we can usually marry or talking about the text data. And I myself is focusing on the text data. And on the bottom, this is an example of how to detecting the named entity recognition. For example, I was given a very long string, and I'm interested in the university part. And then I can detect only the part that I'm interested in. In this case, is the Southern Illinois University. And in this case, I extracted the things that I'm interested in, and I can discard anything that I'm not. Okay? So this is a way to calculate the distance between the different lengths of the words or the strings. Any questions so far? Great. And then we are talking about the, after having the different methods of the things, we are really about the data inputs of the class rings. There are 2 popular ways to measure the data as the data input. They are so-called the data metrics and the dissimilarity metrics. To put it simple, actually, you can directly see the figure. You can see the figure on the right. They are obviously different, right? Maybe you are more familiar with the above one. We can clearly have different features. For example, we are talking about 3 people with different height, weight, and salaries. And due to the time limit, I will say that the advantages and disadvantages for both of them. For the first of them, we can clearly see the features or the parameters of the different classes of that. And we can even easily label that, even label one of them as our feature class or the target class, right? This is very important, and this is very common. In the database, there's one so-called a structured database, or things like that is very easy to curable for that. So this is very popular. However, when calculating the distance, the second one, which is the one in the bottom, which is also very popular. Here we can see that both the x-axis and y-axis, they are all the A, B, C, all the elements. And then all the numbers inside, they are already distance between those things. For example, on the diagonals, you can see that on my mouse are here the first element, which is the first D on the A and A, which indicates the distance between A and A. We suppose they are the same identity, so all the numbers on the diagonals should be 0, right? And on the other hand, all the things are symmetric to each other. For example, the distance between B and A should be the same as the distance between A and B. So in this case, if this is true, we may think that all these metrics are symmetric. Okay? And this, always remember, in your project, there are different assumptions. On these assumptions, this is one of the hypotheses that we can do further calculations. But this is never always true. For example, some of the relationships are not really symmetric. For example, if I lend you some money and I'm calculating this relationship, then the relationship from me to you should be positive and the other side should be negative, if we want to kind of describing this. But there are different relationships. And on the other hand, maybe I am the classmate of you, and in this case, you are together or simultaneously the classmate of me. So in this case, they are symmetric. So you can see that all the relationships, they might be bi-relational or single relational. They are different, but they both happens. Okay? Great. And yes, here we have some examples on this on the right, and we just talk about why we need these two. And then the problem is that it is possible that we can transform from one to the other. And in your case or in your size, which is easier, or both are easier? From the first one to the second one, or from the second one?
First one to second one is easier.
Yeah.
Because when you transfer from second one to first one, some data is lost.
Exactly, exactly. And others agree? Great. Yeah. Two parts. First one is from this matrix into the distance matrix. Then it's easier because as long as you define the distance, you can calculate the distance between the different two elements and get this one, right? However, on the other side, if you have the distance matrix and you want to go back, it's pretty hard because you can never know exactly the height, the weight, the salary. But still, you can try your best to get something like this. And anyone has any idea? There are different things or the different methods we can trying to extract the most important information inside of this distance. We can trying to set the data in the distance matrix and trying to find the patterns inside. And for example, we can use the PCA to find different principal components and then use that to extract back. And always remember that when you goes back, they will never be the same. And they are having different mirror or the different meanings. And in this case, even you get the same things. For example, you do have some hints on the height, on the weight, on the salary, and this is not unique. You can also do some linear regression or the linear combinations of them. For example, I can have the fourth column, which is the height plus the weight. And in that case, that is just a linear combination. Or I can have the height in feet or in inch or in centimeter multiplied by different number. And in that case, the metrics could be different, but they are just the linear transformations. See what I mean? And all of this indicating the difficulties from the distance matrix to the previous one. So that is it. But we can do that. For example, like as we just mentioned, using PCA or SVD, we can always extract the most important features or the principal components and as many as we want, and then use them to direct or to describe those things. And in R, and there's a R application, and we can show about that. I think I can share the application. Online students, can you see now? I'm sharing the R. Yes, okay, great. And here, this is actually from a paper. Let's go from the start. You can see my mouse, and here we're actually talking about the matrix. You can, through the establishment of this matrix, we can see that this matrix is already symmetric. See, this is a trick. I calculate the relationship between them, and then we can see the D here. And this is the D that we just, this is the distance matrix that we just established. And in R is pretty friendly. So after getting a D like this, we can easily plot it. And here they are talking about those different elements having those different parameters and distance and how to plot that in R. And in this figure, we can see that clearly, for example, like W and N are close to each other. And also like C and D are far from each other. Okay. And this is an example to how to realize the distance using the distance matrix. Okay. And then let's go back. And here again, we are talking about these two different types of input for clusterings. I noticed that time is almost there, but I will stop by 5:30 and for some questions. And if you have some other things to do, feel free to stop there. And for all the information that I will now cover in class, you can feel free to see yourself and ask me anything. And here, actually, I do want to talk about some k-means clustering. And for some of you may already heard of the k-means clustering. And this is pretty relevant to the last week, or before last week. We talk about the EM, right? And then we talk about how to do the iterations on the k-means clustering. And for the in-class students, is there anyone who hasn't heard of the k-means clustering before? Is there? Okay. A little bit, but not the same. And here, so I will briefly say about that. And in this case, we will have some dots. Let's take the examples on the figures here. And there are lots of dots or the data here. And in k-means, we need to predefine the k, and which is how many clusters are there inside. And for example, we said there might be 3. And you could also say there's 2, and then you will got the 2 clusters. For example, you said 2, and then you randomly set 3 predefined the things, the centers of that, and might be right, but more likely to be wrong. And in that case, you will try to calculate the distance from each point to the center point that you already defined, and then do the clustering. But that is not always true because the predefined centers are not right. So later on, you are going to calculate the means of the clusters that you just calculated, and then repeat the procedure with the new centers. And then with the new centers, you calculate the distance again and have the new distance or the new clusters. And then until you have the 3 mature clusters. Okay? And this is one way that we already know. And then we are trying to talk about the things that we are not familiar with. And this is also the part in math. And I don't think we have time in class, but always try your best to first cover or do not see this, hide these things, and try your best to write the math functions. And if you fail, and discuss this and see that and how to narrow this or describe this in math. Okay? And the next thing that we really want to talk about is the computation for these algorithms. In computation cost or the complexity, they are the same in this case. That is very hot word or hot terms that trying to disturb or calculate for algorithm. What is the complexity or the computation cost? Basically, we can understand that is like how long it will take to calculate this, or how much space it will take for my memory or the machine or the local things. So we do really want to reduce the complexity or the computation cost. And we can actually imagine that in the k-means algorithm in this case, the big O is the computation cost. It relates to 4 things. The first thing is I. I is the circle of iteration. Okay, and if you are doing more and more calculation or iterations, it will occupy more cost or more room and time. And the second is the point. If you have a data of 100, and that should be totally different than a data set of 1,000,000. Okay, and then is the features. And for all the features, again, there might be different size for that. And last but not least is the number of centers. We say that we need to predefine the KNN, and when we talk about the KNN and K equals 2, that should be totally different than K equals 20. Okay, and in this case, all 4 things are the features that directly occupy or influence the distance or the complexity. And but among all of them, we can never change the iteration numbers because we need accuracy. We can never change the data points, and we can never change the K because that may be of some informations. But we could do something on the features, which is to do the feature selection and reduce the dimensions. That always helps and helps a lot. Okay? And I think time is there, so brief graphs on what's next. There might be other information similar to k-means. There's also a very popular and famous method, so-called the k-meanoids. This one is also popular but different from k-means. Still remember, the k-means use the means of the clusters. And in this case, we do not need to calculate the means. We use the mature data set. For example, again in these examples, we not really need new centers. We always want to find the data set of the exact data in each cluster. For example, in all the yellow clusters, which data acts as the center but already exists. And in that case, the distance is easier to calculate, right? Because all the data already been saved in your database. And then we calculate the distance and have decisions and clusters in this case. And in this case, they are not the means, but they are the centroids. So this is why this method is so-called the k-denoise. And also the math and also the R applications. And in R, there's already a mature package, so-called PAM, which is partition around matroids. And we can, in the R package or in the R file that I uploaded, and you can find the square or the functions there. And last, if we could have time, we can talk about how to better select K using the Albert point, which is very popular nowadays. You can try to find some Albert points research or the papers. And if you can't, you can email me and I can give you some suggestions or references. And basically, that's due to the time limit. That's all. And thank you. And see you. And if you have any questions, this is a Q&A time. And if not, that's it. Online students, any questions? Okay, great. If no, feel free to leave, and I will hang there for a few minutes.